All right, for the concave lens, the ray diagram there, let's remember we had a positive focus for the convex lens that you drew, which means the focus was on the opposite side from the object. We drew ray number 1, should look like that, ray number 2 should look like that, and ray number 3 should look, ooh, that was bad, something like that, right? And so the real rays intersected there, therefore we have a real image. Real images are always inverted, real inverted. This one happens to be not reduced, magnified, because the image itself is larger than the object. Remember, with this particular question, magnified or reduced, I don't care that much about it, not as much as these other two. But let's look at the concave lens. With a concave lens, you have a negative focus, which means the focus is on the same side as the object. So that's this one back here. All right. The three rays we draw verbally are the same, but they're going to look different because the focus is in a different place. All right, so let's start drawing. Ray number 1 starts from the tip of the object and it goes parallel to the principal axis to the center of the lens. And then at that point it says it gets refracted through the focus. The focus is here. So I'm going to put my straight edge from the focus through that point and realize that similar to convex mirrors, the real ray doesn't go through here because this is not reflection, this is refraction. The real ray diverges and goes this way, and it's actually the virtual ray that gets drawn through the focus. So that's our ray number 1 with a concave mirror. Ray number 2 says through the opposite focus to the center, and then it's refracted horizontally. The opposite focus is here. So start from the tip, go to the opposite focus, and remember, once again, the real ray doesn't get there because at this point it gets bent, it gets refracted. And ray number 2 says it's refracted parallel to the principal axis. So I'm going to draw this one parallel, real ray. Virtual ray is what goes back here. That's ray number 2. Kind of a little bit confusing, but verbally is the same. So number 1, parallel, refracted on a line through the focus. Ray number 2, on a line that goes to the opposite focus, and when it gets to the lens it gets refracted parallel. Ray number 3 we get a break because it's exactly the same as ray number 3 for the first one. We go straight through the center of the lens. So it looks just like this. So there's our ray number 3. Remember, ray number 3 is a refracted ray even though it doesn't look like it, so we do put a virtual ray back here. And I should have done that with my straight edge. That looks nasty now. But you'll notice at this point that we have an intersection right here of virtual rays. I'll get closer to even see it. Virtual rays intersect, and so the image of the arrow appears right here. Virtual rays are intersecting, so you have a virtual image. It happens to be upright. All virtual images are upright, and we started the rays above the principal axis, and they intersect above the principal axis. And this one is reduced. These three you will always get these three with concave lenses. Always. It's impossible for a concave lens to form a real image. Therefore, it always has to be virtual upright, and it always is reduced. It's never going to be the same size. It's never going to be magnified. Let's see. There's our convex lens there, the one that I showed you earlier. Image is always smaller. Image is always smaller, sometimes drastically smaller. The first one we did was the convex lens, and that one looks like this. And what we got with the convex lens was this image you're seeing here, this inverted real image. Also note that a real image, we talked about this before with mirrors, but real images can be projected onto a screen. So you'll notice I can project an image. You see an image right now on the paper. That's an image of the lights above. That's actually the light coming through, and you can see the light shining off of the lens right now. It's coming through the lens, it's being refracted, and that real image is being projected onto my paper. If I do the same thing with this convex lens, doesn't matter where I put the lens, it doesn't work. I cannot project that image onto a screen because these only form virtual images. You have to have a brain to see the image that these form. So that was the ray diagram for a concave lens. All right, now we need to move into the mathematics part of this. We've been talking qualitatively this entire set of notes, which means we just describe things in words. Now we're going to use numbers, and there are two specific formulas that we're going to use. In your chart, I think they are number 43 and 44. These formulas you might see at the top of your notes apply to both mirrors and lenses, both of them. So you need to make sure that we know that. The first thing we have to do is understand this table. We need to know with all of our types of optics whether the focus is positive or negative. So remember when we talked about mirrors, mirrors had a positive focus. A concave mirror did, that is, whereas a convex mirror had a negative focus. And it's really important to understand that mirrors and lenses are flipped from each other. The concave mirror had a positive focus, but the concave lens has a negative focus. It's the convex lens that has the positive focus. So positive, negative, negative, positive. Put a star around this table. You have got to memorize this. You need to know this by heart. You also need to know by heart the alternate names of these. And remember that a concave mirror converges light, so it's also called a converging mirror. Whereas a convex mirror diverges light, therefore it was called a diverging mirror. So you will see converging mirror and diverging mirror for each of these, and you need to know that they mean concave and convex. And remember, lenses are flipped. So with lenses, a concave lens is actually the diverging lens, and the convex lens is a converging lens. All right, so really important that you understand that, and you've got to know what these mean. Remember, with mirrors, the positive focus means that the focus is on the same side as the object, whereas the negative focus means it's on the opposite side of the object, or in front of the mirror, behind the mirror. You need to make sure you know what those mean. Whereas with a lens, it means just the opposite. The negative focus means that the focus is on the same side as the object, whereas the positive focus means the focus is on the opposite side from the object. So mirrors, same side, opposite side. Lenses, opposite side. Sorry, same side, opposite side. So it's just slightly different. So it's important that you write all that stuff down. If you didn't catch all that, go back, rewind the video back, and play it again, because you have to know all of that information by heart. You have to know that by heart to correctly do these equations. So to predict the image location, we use this equation, 1 over f plus equals 1 over do plus 1 over di. Do stands for distance to the object, di distance to the image, and f is the focal length. A couple of things you need to know about this equation. First of all, it's really, really cool that this is the first equation all year long that we have not had to convert. You do not have to convert the units in this. It can be in centimeters. Centimeters are what we're going to use most often. But it doesn't matter what the units are because they're all distances. So as long as they're all in the same units, then you're okay. You don't have to convert anything as long as everything is the same. Also need to let you know this plus or minus is there because it's just simply to remind you that the focus could be negative sometimes. It's not a part of the equation, however. So that's just there to remind you, hey, remember to think about the focus because it could be negative. You need to put it in as negative if it is. And if you're solving for the focal length, you will hope to get a negative focus if you're using one of these that has a negative focus. But it's not part of the equation itself, and we'll talk about what that means. DO, another thing you need to make a note about DO is that it always has to be positive to make everything work out right. The distance to the object always has to be positive. All right, and lastly, magnification ratio equation. M equals negative di over do, which equals hi over ho. We've had these before, but hi, height of the image, ho is the height of the object height. You can use either one of these to calculate the magnification of the object. That means how many times it's reduced or magnified. Once again, do, it has to be positive. Once again, you don't have to convert unless the units are not all the same. And then this negative right here, you need to know that unlike this equation, this was not an integral part of the equation, but this one is. We have to leave this negative here regardless of what the distance to the image is. Even if the distance to the image is negative, we've got to leave the negative. So in that case, we would have a negative. All right, so let's look at how these equations work for us. All Alright, so as we read this problem, it's really important that you get used to gleaning as much information as possible. And the first thing I see, it says, if a diverging lens, I can stop right there and know that, remember, a diverging lens is a concave lens, and you should have written down that the focus is negative. So I'm going to tell myself that it's going to be a negative. If they ask me to find the focus, I'm going to hope to solve for a negative focus. If they give me the focus, which they do right here, focal length of 6 centimeters, that's the focus, and it's got to go in as negative. Describe the image formed means give me anything with a subscript I. That means distance to the image, height of the image, as well as the magnification of the image. We're going to do all three of those. Describe the image formed of a 2 centimeter tall flower. That's the height of the flower, which is the object, so that's the height of the object. And the flower is 12 centimeters from the lens. This is the distance from the lens to the object. Distance to the object is what they gave us. So let's start finding all these things. I'm going to start with DI. We have to, actually, because with both of these we have to have DI to get those. DI or HI. So we're going to start with 1 over plus or minus F equals 1 over DI plus 1 over DO. With this equation, it doesn't matter, by the way, which order these two come in. So we're going to plug in our numbers now. The focus they gave us was 6, and remember we decided the focus was negative, so it needs to go in as negative. Negative 6 on the bottom. 1 over DI is what we're solving for, plus 1 over DO is 12 centimeters. Now at this point we have some fractions to deal with. My recommendation is don't mess with the fractions. Don't do that. Just simply put them in parentheses. And if these were numbers, like if this was 6 equals 1 over DI plus 12, you would simply subtract 12 to the other side. And we're going to do the same thing here. We're just going to subtract the whole fraction. So you can do that in your calculator, putting it directly in just like that, in parentheses, 1 over negative 6 minus 1 over 12. It's that easy. Put that in and you get negative 0.25. Now realize that's not your answer at this point. That is 1 over your answer, 1 over DI. At this point, you would end up, you could call it cross multiplication, you would end up multiplying by DI on both sides, whatever the case may be, and then you would divide by 0.25. The ultimate result of this that you can kind of memorize, because we have a lot of equations in this form, is when we're solving for the variable that's in the denominator and there's nothing over here, what you can basically do is make these two switch places. In other words, to get the distance to the image, we now have to do 1 divided by negative 0.25. And if you do that, you get negative 4, and the units here are centimeters because everything else was in centimeters. So the distance to the image is a negative 4 centimeters. Now I want you to realize something about this distance to the image. If this is my lens, actually this ends up being a diverging lens. It doesn't matter though. Remember, our object is always over here. With a lens, the positive side is on this side, the negative side is on this side, because which is where a negative focus would be on the same side as the object. This is where a positive focus would be on the opposite side of the object. Therefore, when we get the negative distance to the image, that means the image is on this side. It's on the same side as the object. That's where the image is. And negative distances to the images, any negative DI means it's virtual. It means it's a virtual image. So it's on the left side and it's virtual. All right, now let's find the height of the image. That's negative DI over DO, and that equals HI over HO. That's the equation we're going to use. We're going to use the magnification part of it in just a moment. That's our distance to the image. It needs to get plugged in here, and remember this negative stays. So we have a negative, negative 4, and those becomes positive. DO is 12. HI is what we're looking for, and the height of the object, the height of the object is 2. At this point, you do cross multiply. 4 times 2 is 8, and that equals 12 times 12 times HI, and then we would divide by 12, and 8 divided by 12 gives us an image height of 0.67 centimeters. All right. This image height actually happens to be positive height, which means it's above the principal axis, and you already know that because virtual images are always above the principal axis. All right. In the next video, I'll solve for the magnification.